this video, we'll take a look at some of the CAN and CANFD security challenges. A CAN network is generally not protected, and as soon as an attacker has unlimited physical access to the wires, then besides just cutting them for stopping all communication, they can install all sorts of sniffers, interfaces that allow monitoring the network communication or even inject messages. On the high end, as soon as there's a remote access device, any device connected that also is a bridge or gateway to the internet, then of course an attacker possibly has full monitoring and injection access from remote locations. That makes CAN systems quite vulnerable as soon as remote access or bridge devices are connected, and in any case, as soon as you put in a gateway to other networks into CAN or CANFD systems, you should have a closer look at the security issues involved. When it comes to protecting CAN or CANopen communication, then there are various methods on various levels that can be applied. In this video, we'll focus on the TLS or DTLS security, which provides end-to-end security for remote access devices or diagnostic devices. DTLS is already a security mechanism well in place and proven in the internet. And in this presentation, we'll check out if and in which cases we can adopt it to CAN communication. It does not make sense really between individual nodes just exchanging a few bytes of data. But as soon as it comes to integrating or connecting diagnostic interfaces that need some authorization, or any sort of remote access where a remotely connected control device can actively connect to one of the or multiple of the devices in a CAN network, then DTLS makes a lot of sense, and we can simply tunnel the communication that comes in via the internet through CAN communication. And in CANopen, or even CANopen FD, it's even more simplified because there's an automatic method for segmentation. Please note that this is not a detailed introduction to TLS or DTLS. There are other sources on the internet explaining how those work. Here, just in a summary, understand that it's an existing security system, also based on X.509 certificates, and so public-private key systems can be used here for initial authentication and opening the channel. Once the channel is established, then typically one switches back to a protection like AES 128. Because that's available in quite a few microcontrollers that have security hardware. So to support that, that makes perfect sense to use during the data transfer. In the end, it comes down to taking these telegrams and the client-server handshake between TLS partners and communicate this on CANopen FD using the universal service data objects. So this is like service data that tunnels the TLS data between the devices. For this use case, we expect that there's a remote access device which functions as a gateway to the internet and the CAN or CANFD system, and that this gateway builds a tunneling the DTLS communication via CAN or CANFD, and in this case here it's used CANopen FD, which provides nicely a USDO communication method that can handle those packages and pass them on to the destination node to provide the end-to-end security. This is the multi-level CANFD security demonstrator brought to you by NXP, Peak, Embedded System Solutions, Keil, the Hochschule Offenburg, and Embedded Systems Academy. It brings together multiple security aspects for CAN and CANopen, and the components are two Peak I/O modules based on the NXP LPC 54618. They are connected here to various input buttons and a sign light post here. And then we have an Android tablet connected via a Bluetooth gateway. So Bluetooth connection to CANopen. And then we have a control and visualizer module based on the NXP LPC 54S018. The S is for extra security, so there are, for example, features like an AES encoding engine in here. And the goal of this demo is to show that we can do remote access, end-to-end security using DTLS and transfer texts encrypted and authenticated to the text display. So the texts will come here from the tablet via Bluetooth to the CANopen Bluetooth, and then via CANopen tunneling to the controller unit and the display up here. To establish a secure connection, we first have to start the app. The goal is to transmit encrypted texts to the control device that then displays it in the display above. So let's first connect on a Bluetooth level and select the CANopen hardware to establish a Bluetooth connection. Remote device connected. We are now connected to the CANopen by Bluetooth. Now we open a DTLS channel, and after various exchanges, the client hello, and wait for the responses, the channel is opened, and we can now transmit text blocks. Here a 53-byte text encrypted data has been transmitted to the Bluetooth module, which then via a CANopen FD tunnel brings it to the control module and displays it up here. And another text, here another text with 80 bytes have been transferred. The reception is displayed here and displayed up here. We now connected a PCAN USB interface between the CAN communication via a Y connector here and our laptop on USB. Let's use CANopen Magic to analyze the CAN traffic. So let's do a connection, network, connect, select the hardware, peak, and the communication rate we use is 500 kilobits and 2 megabits per second. So connect and start the trace, and we already see the CAN communication and CANopen communication in process. So there's quite a bit of communication going on here in the trace. So these are process data flying by and heartbeats. I can briefly have a look at by saying here a fixed display by looking at the heartbeats. Which nodes do we have? So we have node number 2, 4, 5, and 15. In our system, number 2 is the main controller, the display board. So that will be here our TLS server. 4 and 5 are the I/O modules, and 15 is the Bluetooth gateway. So we are now primarily interested in the communication between node number 15 and 2 related to TLS. And let me just enable this as sequence again. So we need to set a trace filter here, configure filter, and we'll enable a pass filter. Say the only thing we are interested in is really the SDO or USDO communication service data, because all the TLS data is part of service data here. So once this filter is enabled, we can see the trace is frozen. I'll do a clear trace here. And on the Android tablet, I'll now initiate an open DTLS channel. And here we can see the communication involved in the negotiation and TLS handshake to open a channel. So I'll stop the recording, go to the beginning, and we can see that node number 15, the gateway, initiated a transfer to node number 2, the TLS server, and sent the request. It took a total of 67 data bytes. This was transmitted in a few segments here because the maximum package size is 64 bytes. And then a little later we see responses coming from the server, and until all the way to the end here, the channel by this time is opened. Let's look at the time involved. So if I go here to the first record and say set timestamp 0 point, then we can see from first to last it took about 790, so a bit less than 800 milliseconds for the entire initiation and opening of a DTLS channel. Now for the pure text transfer, that is no request and response, that is just a single direction transfer. So if I transmit a text right now, so I send a text of 53 bytes encrypted data, you can see with all the encryption involved, it was packed, came up to a total of about 82, was transferred in multiple packages, but always from node number 15 to number 2, and that is the TLS tunnel here used for the transfer. If we do a closed channel, let me just do a closed channel also, I'll clear the trace and do a closed channel, then again both parties are involved and both send the package to that the TLS channel is now closed and it can be resumed later.